characterize the minimal wave speed for this KPP equation, KPP type equation, where the coefficient B of x is periodic with period L. And as I said, traveling wave, U is a traveling wave with speed c, average speed c, if and only if it is written in this form. So this is equivalent to the definition of the traveling wave with speed c. In my previous slide, I put capital L here, but the c is L over capital L, so this is equivalent to the definition of the traveling wave, periodic traveling wave. Then one can easily find a function v of x, z such that excuse me, such that v is periodic in x, and u is written in this form using v. This is the equivalent. This is just a change of variable. So the function v is periodic in x, but in z, as z varies from minus infinity to infinity, x, if you fix t, x varies from minus infinity to plus infinity. So the profile of v with fixed x just looks like this more or less. So it goes to 1 as z tends to minus infinity, and goes to 0 as z tends to infinity. Now we assume that since u of v goes to 0 as z goes to infinity, z is this x minus ct, we make this assumption. And this is true for, generically true for this kind of equation. And actually this, the validity of this formula is already known, so let's assume that this is true. So at the leading edge, u of xt is written by a product of two functions. So separation variable holds for the asymptotics of u. So assuming that u is written in this form, where psi is a positive function, periodic function, we get this equation. So if c is a wave speed, traveling wave speed, this has to hold, this formula. And this is, as I said, this is a generalization of the quadratic equation for the homogeneous KPP equation, in which case psi is a constant. So this term just vanishes, and this is just constant. So you get just a quadratic equation. But this is a more general form. So this is a second order ODE. Now, again, this is the same equation. Again, I remind you that I defined an operator, second order ODE operator, in this way. Then L sub lambda b psi is equal to lambda squared minus c lambda psi, where lambda is some positive constant and c is some constant, some positive constant, but anyway, this is constant. This means that psi is an eigenfunction of this operator L sub lambda b. And moreover, psi is positive. we require upside to be positive in order to be the asymptotics of a traveling wave, because a traveling wave is supposed to be positive. We are only looking at traveling waves that are positive. So this means that mu of lambda b, this means that lambda squared minus c lambda, c is the principal eigenfunction of this second order equation. So if we denote by mu of lambda b the principal eigenvalue of L of lambda b, then it looks like that the minimal wave speed is given in this form. And actually, this is true. You can prove it, but at least intuitively, this is clear, because for a constant, positive constant c to be a wave speed, this has to be satisfied. Of course, under certain ansatz, the validity of those ansatz are already known, but I don't prove it here. So let's just assume that those asymptotics really hold, and then we have this, and then it is clear that psi is a positive eigenfunction of this operator. So for c to be a wave speed, there must exist some lambda such that mu of lambda b equals lambda squared minus c lambda. So this is a necessary condition for c to be a wave speed. But actually, one can show that it is also a sufficient condition, and to do that, one has to work more on the original PDE and super subsolution argument, for example, and other arguments. Sometimes you can also use fixed point argument to show that if C satisfies this, there does exist a traveling wave. So far, we have only analyzed the leading edge, but it turns out that this condition coming from the leading edge is sufficient to guarantee the existence of a traveling wave. So let's admit that this is true. This is already well established. Then the minimal wave speed is given as an infimum of this, and actually this is a minimum of this set of C's. Here, the difficulty here is the following, as I mentioned in the morning. So what is this eigenvalue? The operator looks simple, but there is b of x here, which is a given periodic function. If this is constant, then it is very, very easy. You can obtain eigenfunctions. Eigenfunction of this is actually constant. The principal eigenfunction is constant. But if b of x is not a constant function, then it is difficult to characterize directly the eigenvalue and eigenfunction. And why it is difficult? Because of this term. Because of this term, this operator is not self-adjoint. And as I mentioned this morning, if this were, the boundary conditions were Dirichlet or Neumann on a bounded interval, then by a change of variable, you can convert it into a self-adjoint operator in some weighted L2 space. So you can use standard variational formulation to characterize the principal eigenvalue. However, this is not possible. This is not self-adjoint in any weighted L2 space, and indeed, because of the periodic boundary conditions, complex eigenvalue can even appear. So there is a big difference between Dirichlet-Neumann boundary conditions and the periodic boundary conditions with the first order term. So you can never erase it by a change of variable. If you want to erase it, then periodic boundary condition will be violated. So, but apart from this difficulty, one has reached the characterization of the minimal wave speed in terms of the eigenvalue of this operator. And this is studied in Beresty-Kamel and Beresty-Kamel-Rock or Nadirashvili, Weinberger. Weinberger does not write it down explicitly, but from his abstract theory, the same principle follows. And it turns out that also in this periodic case, C star B turns out to be the spreading speed, which is already studied by Freitling in 1984 for the spreading speed by a probabilistic method. And in the KPP, homogeneous KPP equation, I used this, I showed some formal derivation of the spreading speed by linearization and using the heat kernel. But you cannot have a heat kernel for this because of this B of X term. But using some sort of a probabilistic method, you can do something similar. Then you can get spreading speed which coincides with this minimal wave speed. But approaches are different completely. Then there is a work by Shigesada Kawasaki Teramoto. They are Japanese ecologist, mathematical ecologist. They made a very, very interesting observation from the point of view of ecology. So what they did is the following. They probably did not know the work of Freitling, so they tried to study, and Freitling did not have the formula for the traveling wave anyway. So Shigesada Kawasaki Teramoto tried to study the minimal wave speed for the following particular problem. In their case, B of X is a periodic sequence of step functions. And B of X, okay, in their case, they studied F is like this. It's a bit different, but analysis is completely the same. Analysis for the wave speed is the same. This and this basically the same, because all you all you need is the derivative at u equals 0, derivative by u, so it's the same, bx. Now, b of x, in this situation, in this setting, it's carrying capacity. But anyway, B of x in this context, this is the derivative of f of x at u equals 0. So this is the growth rate of the species when the population is very small. So roughly speaking, to be more precise, b of x times f prime of 0 is the growth rate. But in this case, f prime of 0 is b of x itself. So so b of x itself is that. But in this case, I might have forgotten. No, I didn't. I normalized f so that. Okay, I forgot to say this. F prime of 0 is equal to 1. I normalized it. Otherwise, you have to put f prime of 0 all the time after b of x. Just for notational simplicity, I normalized it. Just by change of variable, you can do that. So f prime of 0 is missing here, but because it is assumed to be equal to 1. So then it is completely the same situation as Shigesawa, Kawasaki, Teramoto. And this is the natural growth rate when the mass is small. Population is extremely small. So what does it mean? There be the area where B is let's say it is 1 here and 0 here. This is a favorable region for the species. And this is unfavorable. So suppose that this kind of favorable and unfavorable regions appear alternately, periodically. For example, if the species live in forest, this is where the trees are located, and this is a river or road where there are no trees, so they cannot live here. In order to spread, they have to cross a river or road, and this will sort of slow down their propagation. And here it accelerates. So the speed is fast here because it's favorable, and the growth rate is fast. Then the growth rate is bad again, and then good again. What they wanted to study is the following. In this particular case, b of x is constant on one part, and another constant on the other part. Suppose that this ratio is alpha. Okay, so this is alpha L. Alpha is the ratio of favorable regions of the unit length, unit period. So let's fix alpha and change L. This is what they studied. So by which I mean, suppose that favorable and unfavorable regions are just repeat in very short period like this, or intermediate period, or very large period, but always the same alpha. In this case, the bad area is short, but the good area is also short. So it changes. It changes very, very frequently. So it looks almost like constant. This one, the good area lasts for a certain period, certain length, and then bad period, not very short, not very long. So it repeats. And if L is very large, then there is a long range of good area, but also a long range of bad area. They studied which one gives the fastest speed of invasion or propagation speed. So they calculated explicitly C star beta. Well, in order to study C star beta, what do we need to do? Okay, let's look at next picture. So we want to find C star beta and C star B, and B is given. In order to find C star, we change C. Then as C gets smaller, it goes like this. So then there is no lambda for which these two are equal. So the graph, this is the graph, B is fixed. This is the graph of mu of lambda B, this principal eigenvalue, as a function of lambda. And these are parabola, this one. They have to have a root, this equation. So then this one is the parabola for C equals C star. For C smaller than C star, there is no intersection, so therefore it is outside of this set. So this is how C star is characterized. Therefore, if you know this graph, this curve, a graph of mu of lambda B precisely, explicitly, then you can calculate the C star explicitly. And this is the case for Shigesada Kawasaki Teramoto case. You can compute mu of lambda B as a function of lambda explicitly, because all you need is just compute this eigenvalue of this operator, where B is a constant on one side and 0 on another side. Then you can compute explicitly by using exponential function, because it's a constant coefficient, but constant changes suddenly, so you have to match them. But the computation is not that difficult. All you need to pay attention to the matching condition here at the boundary of favorable and unfavorable region, and inside of each region it's just exponential, and suddenly the coefficient changes. So it's not a very difficult computation, but the outcome was very interesting. So they computed the first mu of lambda B, and then computed C star. And this function B is this, so it depends on L. So they varied L. This and this and this. Which one gives the faster speed? Okay, so who thinks that? Okay, who thinks that this one with the shortest period gives the fastest period, fastest speed? Okay, and who thinks that the longer period L gives the fastest speed? Okay, so 0. And here 2 or 3 people, and the rest is this. That's wrong, completely wrong.
Give us one more chance.
Okay, so who thinks that this is the fastest? Okay, so anyway, by the way, the last part, the proof existence of traveling waves and the proof of this cannot be obtained from the result of Henri Beresticky and his group, because they studied only reaction diffusion equations with a smooth coefficient, or at least bounded coefficient. So we needed to use some other results, and it turned out that Weinberger's result, which appeared in the same year, which is interesting. You know, sometimes some very good papers, very good result appear at a different at different places about the same time. This sometimes happens. It appeared in the same year. His result is on monotone operator. Monotone operator, very abstract. Therefore, he didn't need any smoothness. And this was very useful. So the last part, we used Weinberger's result to prove that this eigenfunction characterization of the minimal wave speed for the major coefficient, we applied Weinberger's result. Now let's explain the variational characterization of mu of lambda b. And as I said, L is not self-adjoint, so standard characterization doesn't exist. However, if you make a little trick, you can characterize it variationally. So this is the result by Nadin, Grégoire Nadin. And mu is given as the minimum of the following complicated functional. Okay, first of all, eta varies in H1 period means that it is a H1 function which is periodic with the period L. Then this first term is a standard functional, the same as this one. Standard functional for the self-adjoint case. But there is additional lambda. What is the role of this lambda in the eigenvalue characterization? It is here. It is a bit strange here. Integral eta squared is okay, but here comes minus L squared over integral eta to the 2. It looks a little strange. But by Schwarz formula, Schwarz inequality, this part is positive, non-negative. You can check it. This is another way to see that the presence of lambda increases the eigenvalue. So h of eta is I is the interval of length L it looks a bit complicated, but you can easily check that this gives the eigenvalue, principal eigenvalue. But principal eigenfunction is not given by eta itself. The principal eigenfunction is given by this form, where psi is a solution of this. So this is the difference from the standard variational formulation. So minimizer of this H does not give the eigenfunction directly. By the way, this symbol means the average. This is average. If you integrate this right-hand side, then the integral from 0 to L is 0. Therefore, C is indeed a periodic function. If you just look at this, if you replace lambda by minus lambda, it gives the adjoint operator. And adjoint operator and this operator L, the form is the same. But of course, it's Fredholm result. The adjoint and the operator itself has the same eigenvalue. So this is no surprise. But this well-known result of Fredholm is explicitly shown here in this formula. And the only difference between L and its adjoint operator is that you give minus lambda here. The same eta, because eta is unique, same eta, but different psi. If you change lambda into minus lambda, this new function is again periodic, and it is the principal eigenfunction of the adjoint operator. So adjoint operator and original operator, the eigenfunctions are given in the same form, only the sign is different. This turned out to be extremely useful. I don't prove it here, but anyone, if you want, I can send you Nadan's original formula is written slightly in a different manner, but I can send you my paper in which this is proved in one page. It's not difficult. Anyone here can check it by tomorrow by himself or herself. It's not too difficult because all you need is just differentiate it and look at the Euler-Lagrange equation, and it turns out that it is indeed it gives eigenfunction. But eta, the difficulty is that eta itself is not eigenfunction. You have to think of this way. This is the little trick. But once you know that, it is not too difficult to check. It doesn't take more than a day for anyone who knows calculus, some advanced calculus. And how was it used? Okay, Nadan, in the case of Nadan, the result of Nadan is the following. He used this useful formula to check Nadan's result. He also looked at a similar problem. Again, in the same year, a similar result appeared. In his case, B0 is given. Okay, B bar no, okay, B0 given. And B star in this case, no, sorry. Consider B that is equimeasurable. So consider this set. Equimeasurable means that if you have a periodic function, just look at one period. Everything has to be periodic with the same period. So all you need to look is one period. Two functions being equimeasurable means that their distribution function is the same. For every level, this length, the sum is the same as this one. This is called equimeasurable. So which means that all you need is just deform the graph horizontally, not vertically. Then you get equimeasurable functions. Then maximize C star B. Fix B0 and consider all B that are equimeasurable for B0. Which B gives the fastest speed? So he considers this. And then the conclusion, okay, let me just explain his result before going into the two-dimensional problem in the next lecture. Next lecture will be for two-dimensional problem. So his conclusion, answer, this maximum is given by Schwarz symmetric rearrangement. Or you can call it symmetrically decreasing rearrangement. He calls it Schwarz. What does it mean? Schwarz symmetrization or symmetric decreasing rearrangement is the following. Okay, this is B0. Schwarz rearrangement of B0. So what is it? This is B0. We just look at the one period 0L. Schwarz rearrangement is this. It is symmetric. So this is B0 star. This is Schwarz. It is symmetric and decreasing. Symmetric and decreasing. And equimeasurable to original B0. This is unique, of course. Once B0 is given, B0 star is uniquely determined. This and this are equimeasurable. Okay, maybe I have to make it a little fatter, like this. This gives the maximum speed. Why? Because if you look at this part doesn't change by varying B. Only this part changes. This is independent of the choice of B. Then by the well-known inequality of rearrangement, eta prime squared, this L2 norm of eta prime, becomes smallest if eta is also symmetrically rearranged. Symmetrically rearranged. And if B of x and eta of x are both symmetrically rearranged, so this becomes the largest. Both have the same peak at the same position. So this becomes largest. So this becomes smallest and this becomes largest. So the whole thing becomes smallest. If mu becomes the smallest, just remember, suppose this is mu lambda B0. It becomes smallest with B0 star. Then you have to choose larger c to reach it. So the minimal speed is increased because the graph goes down. The graph goes down means that you need a larger seed for the parabola to reach. So it all comes from here. And this part is the standard function. So the known result for the standard variational calculus that. In my lecture, next lecture, I will discuss other things, other application of this. Nadan looked at this part of his formula. We will look at this part of his formula to prove the monotone dependence of the planar wave speed with respect to the angle. And this I will discuss tomorrow morning. Thank you very much for your attention.